I didn't hear the, there it is. Okay, never mind. Thank you.
Got it. Okay, can you just confirm that you can see the slides?
We can see it, yes.
Okay, thank you very much. So, first of all, I just want to spend a little, few words about my work with Peter and just about Peter in general, because I think that probably the students that are attending didn't get the chance, they weren't lucky enough to meet Peter, who was honestly, when I was doing my PhD, sort of one of my idol, I would say. I think that still today, I think that among the best papers that I've read in mathematical finance have been written by Peter and other co-authors. So when I got the chance to work with Peter, I was super excited. And the reason that our collaboration started is that when I was doing my PhD, I studied compound options, and Peter was interested in this type of subject because I would try to convince you that despite these are strange derivatives, they are actually quite helpful in other pricing problem. And so everything started as a collaboration, and as time progressed, we worked together for about 1.5 years, and then what we know happened, and I was I had to finish this work by myself, and I hope that I made him proud of what we started, that I had to conclude myself. So as you can see, the title is a quite long title, and thanks to the referee who made me change the title, because my original title was a little bit shorter. But essentially what we're going to do in this talk, I will lead you through compound option under some let's say exotic distribution that Peter and another Italian researcher, that is Torricelli, introduced in a paper. And we're going to study how the pricing of these compound derivatives are conducted under these unfamiliar distributions, which I believe have some pros compared to other, let's say, competing distribution. And then we apply some of the results to the pricing of a specific contract, which is a traded contract, which is an American option written on an asset that pays a discrete dividend. And this actually, it's the so-called Roll-Geske-Whaley formula that was published, I think, in the 80s. And so we tackled the problem with a different type of distribution. Okay. So in terms of summing up what I just said, the main question is whether it is possible to price compound options that, for the people that are not familiar with, are essentially options written on options under the newly introduced distribution that Carr Torricelli in a recent paper introduced. And as side quest story from this journey, we wonder whether this formula could be somehow elementary. What elementary means? Elementary essentially means that you can compute it using just a standard simple calculator. And Peter was very fascinated, I think, about this aspect of the pricing problem, because, as you know, let's say the simplest model that we can think of for pricing option is the Black-Scholes model, which, of course, you can price easily with MATLAB, Excel, any type of, let's say, software that has some built-in function. But let's say if I give you a calculator, you will not be able to price an option. On the other hand, these distributions that Carr and Torricelli introduced in this paper in Finance and Stochastic produce prices which are elementary. You just need a calculator for computing the price. And then, as I said, once we established the pricing of compound option, we can look at the problem of the American call on the asset that pays a known dividend and see what we can do on this side. Just like to the student that I'm sure that they are aware of this, but we know that in general, there is no up-to-date closed form formula for pricing American options. There are some specific American options that you can price semi-analytically, but in general, the pricing problem is a difficult one to solve. So let's say that the problem is still open. Like if you're able to find a pricing formula that you for pricing American options, general American options, you would be praised by, I think, many people. Other parties that remember that the price of an American call is the same of the price of a European call, only in the case the underlying doesn't pay dividends. When you have dividends, whether it is a discrete dividend or you have, let's say, a continuous stream of dividends, the price, you cannot resort, like you cannot use, let's say, the standard European one, but the price will be different. And in fact, in this case, we have a call on an asset that pays a discrete dividend. So the pricing problem is still achievable, but the price of the American will not coincide with the one of the European.
Federico, this is Leon. Hi, hello. I have a question for you. Hi, regarding your third bullet point on the prior page, right?
Yes.
Are you suggesting that there's some mysterious way to think about an American option in terms of it being sharing some attributes of a compound option? You're not suggesting that, right?
Well, I mean, the Roll-Geske-Whaley formula is a way for pricing this American call written on this asset that pays a discrete dividend and uses a portfolio which inside has compound options.
Oh, I didn't know that. Oh, interesting. Okay. Right.
Yeah. Like this is one of, like, I think this is one, like, still today, like before I like this paper with Peter, this is one of the few cases where you could actually price the American call on an asset that pays a no discrete dividend, which, I mean, in the real world, it's not something that you would know because you need to know the dividend, and dividends are random. So like, I mean, but I would say that it serves as as every model as an approximation of what we see in the real world. And funny enough, at the conference, at the Memorial Concert of Peter, I met some option guys from Amsterdam that used let's say, generalization of this formula on compound option for assessing the price of options written on the index that pays sort of known dividend, if at least not known, but they know when it's going to be paid. So it is something that is like even used by practitioners for some specific cases, at least as a reference for like doing some sort of like assessment about the prices.
But it's far from what you would call a static replication of the American option with a European style compound. It's very far away from that ultimate situation, I guess, right?
Well, but this is actually like, I will show you this, like I will put the result of the Roll-Geske-Whaley, and what they do is actually a replication of the payoff with a portfolio which is long a call, long a call on call, and short another call. Okay, and this is actually like, it is a static replication, just having like the idea why, the reason why you can do so is that since you have a non-discrete dividend, you know that the only point in time where it would be optimal to early exercise the option is just right before the dividend is paid. Right. So essentially you have solved indirectly the boundary problem on when it is optimal to exercise. So in that specific case, you are able to do something more. That's the only reason why you can do that.
I see. Thank you.
You're welcome. Okay, so just a brief outline. So what I'm going to do first is give you a quick introduction of this like mysterious distribution that Peter didn't discover, but like brought this distribution into finance, and they all come from this Dagum distribution. Then I will move to the pricing of the option, the pricing of the compound options, move this results onto this pricing of the American. And then I have just a small, relatively small final session where I talk about what Peter liked the most about this type of distribution and problem, which was the whether under which condition this formula are elementary. So let me just state clearly that for the simple, let's say, calls and put, vanilla call and vanilla put, under this Dagum distribution, the price is always elementary, okay? For the case of compound options, this is not the case. You can still rely on semi-analytical formulas, but there are some choices of the parameters which would allow you to make the price elementary. And I think that despite these parameters could be absolutely, well, I don't think they are that arbitrary because there is sort of a symmetry in this model. So there are some specific values that I'm not surprised that these are the values that make the pricing a little bit simpler. But it's still fascinating, I think, that you are able to do so because there is no such way you would be ever able to do this in a log normal model. Okay, so just again, very quick on the related literature. The main paper that it's based this work on is the Carr and Torricelli on finance and stochastic, okay, where they propose this alternative distribution for vanilla options. And then there is all the literature about compound options that you may wonder, why do I care about compound options? They are not traded assets, so why should I care? Well, the reason for caring about compound options is that if you see equity as an option on the asset, then vanilla options become compound option. And this is all the literature started by Roll-Geske at the end of the 70s. Then you would also maybe using compound options for modeling some sort of structural model of credit risk. There are other instances, except for the Roll-Geske-Whaley formula, where compound options are linked to American options. And there is another paper, let's see the last one, which is Prekova, Zantai, which also use compound. In the specific case, they use n-fold compound option for approximating American claims, as well as some other exotic derivatives. But without like further ado, let's start with the actual need. So this Dagum distribution is going to be the cornerstone of the work that Peter started with Lorenzo Torricelli, and then we continued with myself. So we say that a Dagum random variable is a random variable x, which depends on three parameters, m, p, and q. They are all positive. And you can see that for this distribution, you can explicitly write both, well, the probability density function as most of the distribution you can, but also the CDF is not just an integral, but you can like explicitly compute solve for the integral, and you would get an analytical expression, an elementary expression for the CDF as well. So as I said, that this is a random variable which is positive. Okay, so the main idea would be we will be using some modification of this variable to model prices, which we assume to be positive. Okay, and in the specific, the parameters of the distribution are m, which controls the location, and it represents the mean if the value of the parameter p is larger than 1. Okay, p is something which relates to the concept that we have about standard deviation. Is not a standard deviation, but is something which we call, it's the precision, okay, which means that actually 1 over p controls the dispersion of this distribution, whether Q controls the skewness of the natural log of X. And you would have that you can have distribution which are either positively skewed or negatively skewed based on the value of Q. And I think this is one of the appealing, let's say, feature of the distribution, because it's not, is a distribution which is very tractable, like from the perspective of the PDF and the CDF, and allows you to easily control the skewness. And as we know from empirical evidence, financial returns are usually negatively skewed. So we will try to use a distribution which has a finite mean, because this is what you want, as well as it is negatively skewed. So this is the building block where we start. Then I now introduce two more distributions which are connected to this one. This one is the skew-logistic distribution, which is indeed connected to the Dagum distribution with, let's say, the last equation that you have on the bottom of the page, which says that if X is Dagum, the ln of X is skew-logistic. And you can easily map the original parameters onto the new distribution, just in the way that you would see there. And the same spirit for the Dagum, you have both elementary functions for both the PDF and the CDF. So again, as we said, if we say that the prices are Dagum, this is just to say that log returns would be skew-logistically distributed. And finally, there is this other distribution, which it's interesting that because it will come up in a strange way in our problem, which is the sigma-Dalla distribution. And it is essentially the distribution of 1 over X. In terms of financial interpretation, the only thing that I have in mind for saying what is this sigma-Dalla, if you think that X is actually a exchange rate, let's say foreign to domestic, 1 over X would be the domestic to foreign, but nevertheless, this distribution will not really appear in a, we will never say that a price is a sigma-Dalla in the specific case, but it will show up when we do a change of measure. So it is important just to have in mind that is more, let's say, more a technicality, is a distribution which is needed for carrying out the pricing. Okay, sorry. Okay, I've introduced this tree distribution, but we are almost done. What we want to do now is constrain or reduce the dimension of this parameter space. So what we're going to do, we're going to link P and Q of the Dagum distribution, making them Holder conjugate. This allows you to just result on one parameter, which we call B, which is 1 over P, which means that 1 minus B is going to be 1 over Q. So we say that X is distributed as a sigma-Dalla with mean, well, with location parameter M and coefficient B that we will call after bewilder, but Peter called this bewilderment. And if we start from a Dagum and we set 1 over P equal to B and 1 over Q 1 minus B. Setting the parameters in this way will exactly achieve what we want. So we will make, first of all, the mean finite. Okay, so the mean of the distribution is actually M, and we will make at the same time the log of the price to be negatively skewed. So this is a distribution with finite mean, negatively skewness, as well as mild excess kurtosis, which are all three features that you would like, I think, to have, or at least to account for in a model, just based on the fact that this is the empirical evidence that you would have from prices and returns. So everything, as the title of the talk is, compound option pricing under the Conjugate-Power Dagum distribution. This is the main building block that we will be using. So now we start with the assumption of the model. These are very, like, let's say, standard assumptions. You start with a filter probability space, okay? You assume non-arbitrage condition in, in the economy and the existence of the equivalent martingale measure Q, which is equivalent to the real world measure. In the same spirit of what they do in current Torricelli, we assume that there is zero interest rate, just to make the calculation a little bit cleaner, okay? And then we assume that under the martingale, the equivalent martingale measure, the prices of the underlying at maturity is distributed as a conjugate power Dagum random variable, okay? As we said, we will parameterize this B as a B of T, thus allowing to have sort of a term structure, if you want. And the only thing that, so it sort of, it is an halfway local vol, if you want to think it. You don't have the K, you have just the T, okay? And the idea is that as long as this B is in 0, 1, you're fine. And the only requirement that you need is that as you approach maturity, this B tends to 0, okay? Then another, like, let's say, a practical problem is how you would connect this bewilderment function to the usual concept of volatility. And like, to ensure that you have this limit that goes to 0 and that it is bounded at 0, 1, Carr and Torricelli proposed this map. There are other maps that could work. I think this is the one, the easiest one that you can probably think of. This is, when I go through the talk, this is something that is relevant for what I do up to a point, but I would say that there might, I'm not saying this is the best way to parameterize volatility to be. It's just one feasible one, okay? And there might be other that are better, actually. If you have some other idea, feel free to share with, like, to share, because like this is a, you will see a caveat of the model, but let's get into it. I just want to make sure that this distribution is actually risk neutral, okay? Which is, I just need to prove that the expectation of ST is equal to S0, okay? You can do the calculation, solve the integral, and you indeed find that this is risk neutral. So this is the main idea. Another part of the story, which is, I mean, it's not written in here, but you need to a little bit reverse the way you do pricing. In a way, normally when we talk, also when we student learned, you assume a process, okay, driving the underlying, and then you get marginals, and with this marginal you do the pricing. Another way around of this, and this is what Carr and Torricelli do in the paper in Finance Stochastic, is that, okay, let me find the marginal which is consistent with risk neutrality, and I will try to do reverse engineer and find what is the process driving these marginals. You can do this, okay? So this is just to say that normally we pose a process, but for vanilla option, the only thing that actually matters is the distribution at maturity, okay? And for compound options, which is a path-dependent option, this is not true anymore, but it's not as bad as for American option, because essentially in compound option, as we shall see, what matters is the distribution at 2 points in times, okay? Only 2. I don't need to know the whole distribution across the whole between 0 to capital T. I just need the 2 specific times.
Okay, but question, as far as calculating the mean of the distribution to confirm that it's risk neutral, I mean, the original Dagum has 3 parameters, right? Is that correct?
Yes.
CPD has got 2, right?
Yes.
Right. But aren't you already, when you write CPD parentheses S0BT, isn't immediate that the mean of
I just wanted to convince you. Yes,
okay.
you're absolutely right. I just wanted to convince you and show you that I wasn't, that, like, let's say, restricting these parameters. I'm not cheating. This still works, but you're absolutely right. I could have skipped this, but this is just for showing that this is rigorous. Okay.
But in the prior page, when you define the P and Q relationship, right? 1 over P plus 1 over Q equals 1, right? That
Mhm.
relationship between, that doesn't say anything about the M, right?
No, absolutely.
Okay. So then when you say that the first bullet point, as P is 1 over B, the mean is equal to M. I mean, that's like, it's M because it's M, right? There's no connection between the P and the M.
Well,
that
there
what-
is a there is a connection.
Okay,
Because the mean is going to be M only if P is larger than 1. If P
Oh, I
is
see.
between
Okay.
0 and 1, the mean doesn't
Doesn't
exist
exist.
because it
Okay.
goes to infinity. Okay.
Right.
So
So
this is
since
just
you know
to
that,
show
since
that
you
the
know
mean.
the P is bigger than 1, you can assert that M will be the mean.
Yes, exactly.
I see. Thank you very much.
Next step, we talk about this object which Peter decided to call merit put, because essentially it is the put plus the underline, but just to, it's the usual portfolio that you would be using when you want to prove the put call parity is the maximum between ST and K. So it is the maximum between the price of the underline and maturity and the strike. Okay, which we know it is either a portfolio of call plus cash or put plus underline. Okay, which at the end of the day, is the only thing that you really need for pricing options. This is the building block of option pricing, despite in textbook, you would start with the payoff of a call and then the payoff of a put, but this is what you really need. Like once you know how to price this, you can price both put and call. So the first equation tells you how just to write this in terms of indicator function, which makes the pricing nicer. Then you take the risk neutral expectations, and you will end up with the expectation of ST times the indicator function, then the underline is larger than K, plus K times the risk neutral probability that ST is less than K. Then we're going to use a simple trick of changing the measure from the equivalent marketing error measure to what is called the spot measure, which is just the measure that uses, instead of the bond, it uses the underline as numeraire. And this just allows you to write let's say, this, I hope you can see the mouse moving, the price in terms of S0 times a probability of ST being larger than K under this measure plus K times the probability of ST being larger than K, being smaller than K under the risk neutral measure. And as I said at the beginning, then you can price calls just having the value of the merit put minus K, or puts having the value of the merit put minus S0. And just this, so far, like I didn't say anything about the conjugate power Dagum, anything. So this is fairly general, whatever distribution you are using as your distribution for the underline at maturity. So I show the usual case, which would be the Black-Scholes model, at just saying that the underline is log normal, okay? And this is done in a, I would say, instructive way, just to show you that things change quite, I would say, significantly once you move from the normal world, where everything is sort of nice, to some other distributions. So in the specific, usually in the Black-Scholes world, you assume that the log returns or arithmetic returns are normally distributed with a given mean and a given variance function, okay? And what happens when you change the measure from Q to Q hat, you're just essentially shifting the distribution, okay? So under the Black-Scholes model, change of measure preserve distribution and just changes the mean of the distribution. Once you have the two distribution under the two measure, then calculating the probability is fairly straightforward. But you need to rely on the CDF of a standard norm, which we know is not an elementary function, but still we always write, let's say, PD1 or ND1, ND2, and we almost like forgot that these are integrals at the end of the day, okay? And this is just usual standard Black-Scholes pricing of the merit put, which is not elementary. And we lived like fairly like with no problem up to this day with this thing, which I think is we can still keep on doing this. On the other hand, we have the conjugate power Dagum case. I told you what is the distribution under Q, but I need to tell you what the distribution under Q hat. So what you will be doing, it's using this trick of applying essentially a Lorentz curve to the CDF under Q to obtain the distribution under Q hat. This is very general. You can do this for any distribution, for which you can calculate the integral. You don't do this under the normal one, just because this is not helpful in the normal case. But I think that if you like, just to see this, at the end of the day, what I have here is the expectation under Q that I can write as S0 times Q hat. So if I want Q hat, it's just the original expectation over S0, and this is essentially what is written here, okay? Nothing more than that. The difference is that in the specific case here, I can do this analytically. So what I find is that if you solve for this integral, you would find and recognize that the CDF that you obtain is the CDF of the conjugate power sigma dalla. And this is why I said this is not a distribution that we use directly, but that we will be using indirectly when we need to perform the change of measure. So now that you have the probability under Q hat, you can just plug in the numbers, do some calculations, and what you get at the end is the price of the merit put, which is elementary, because you can, if you know B, you can calculate this with a calculator. And I think this was something that Peter was really after when he started this project with Torricelli. And I think this is interesting. And now I show you something that I think it is, I think the one of the catch part of this idea is this one. So like we've seen that the merit put price essentially is an LP norm, with P 1 over B. But this should not be that surprising, because in a way, the payoff at maturity is an L infinity norm, is a max function. So what pricing today means, just means reducing the index of the norm. And in fact, what you do in terms of of the assumption of the model is that BT goes to 0 when T goes to 0, which is exactly when T goes to 0, it means that I'm approaching maturity, and I have that this limit goes to infinity. So my actual order of the norm converges to the L infinity norm. So in a way, this is not something that you would see as straightforward in the Black-Scholes model. This is something that is instead, I would say, naturally embedded in this distribution. So, and this is, I think, something that I will be working on in the future, because I think on this idea lie probably the either success or failure of this distribution, because this, I think, this is a very strong link between prices and payoff from an algebraic perspective. So, and I know that there is Umberto Carbini that has been working on this, and I'm in contact with him for doing some work. But this is just part of the story. Now, let's move to the compound. So I will be relatively quick. A compound merit put is a merit put written on a merit put, and the idea is that we apply the exact same ideas before. So the last line of the slide, to price this, you need to have the expectation of the merit put at times T1 with maturity T2, plus K1 times the probability that the merit put is less than the strike of the merit put. As you want to express everything in terms of the underlying space, which is ST, you want to write essentially the indicator function, not have the merit put, but you want to have S as a variable, which is something that you can easily do in this way, because the merit put is an increasing function of S. So for every K1, there is a K star, which will essentially translate the problem from the merit put space to the asset space. So this is the way you would be writing this. And again, this is, let's say, model free. I didn't assume anything about the distribution of the underline. We know that, however, that K star is, of course, model dependent, and it will, in the case of the log normal, must be computed numerically. In the case of the Conjugate-Power, Dagum is instead elementary, as I will show you. And now let me just put some caveat on the pricing that I will be doing. So first of all, I'm not really using, so now I need to have sort of a process, because as you see, this payoff depends on two times, T1 and T2. So I need to have some structure. And what I'm going to do, I'm not going to use the underlying process in Carr and Roll-Geske-Whaley. The reason why is that they find that process, so at every time T, the marginal is Dagum. This one is it's fine for what they have to do in their paper. What I have to do here, this will lead you to very nasty calculations. What I'm going to do here instead is using a much simpler process, because I don't need essentially a continuous time process. I just need a discrete time process where I know the distribution at T1 and T2. And what I'm going to model are the essentially geometric returns or price ratios between T1 and T2. And the reason why you use price ratio is that under this distribution, divisions work a lot better than subtraction, which is, I will convince you this when I compare log normal with Dagum. And most importantly, what I have to do is I need to set the distance between 0 and T1 and T1 and T2 equal. The reason that I have to do so is that I need to rely on the same bewilderment function, which depend on the time to maturity, or it depends on the time step. This is definitely a big assumption, or at least it's very restrictive, okay? In a sense, I will be able to price only compound option that have, in which the underlying option expires halfway through the goal maturity, okay? But there is nothing that I can do about at this point. And at the end of the talk, I will actually tell you something about this and the way I'm thinking I can relax this. But so far, this is the best that we could do. So in the log normal case, what you do essentially is that you assume that log returns are normal distributed and they are IAD. So the distribution between 0 and T and between T and 2T is the same normal distribution. And the nice thing of the normal distribution is that if you want the distribution over the full interval, this is just a normal distribution, nothing more than that. And because the sum of normal is normal. But this is, like, I think this is something that sometimes we forget, that the luck and like extreme success of this distribution in every field of applied sciences or like any whatsoever is actually what probably one is this one, that the sum of normal is normal. Okay, so in the case of log returns, I know what is the distribution of the increments, then I know the distribution of the full path. And this is a very particularity of the normal distribution that other distributions don't share. Nevertheless, you do the pricing, you would see that the compound merit put, as well as compound option, as you are aware, depends on bivariate normal distributions, okay? So this phi 2 is the bivariate CDF of a normal random vector. Again, there is no way this is going to turn to be elementary, no matter what parameters you use. On the other hand, for the conjugate power Dagum case, I'm looking at geometric return, so price ratios, okay? And what I do is assume that our IID conjugate power Dagum, okay? However, these are the distribution of the steps. The total return of the full period would be the product of these two. And unfortunately, the product of conjugate power Dagum is not conjugate power Dagum. So, but the good thing of this, even if I were going to use, let's say, arithmetic returns, so log returns, I would have the sum of skew logistic returns. The sum of skew logistic is not skew logistic. So we are like, it's sort of a dog that is biting his own tail. So I need to give up something. And what I'm willing to give up is essentially having a different distribution at the end of the period. The good thing is that if you assume this, despite the distribution at the end at 2t is not conjugate power Dagum, I'm still able to find the CDF of this distribution. So especially equation phi is telling you that if you are in this setting at time 0 and you want to price a merit put with maturity 2t having 2 steps, this is not the formula that you've seen because the distribution at time 2t is not conjugate power Dagum. However, if you place yourself at time t and you look t ahead, what you will have is the usual formula. And this is what is nice about it. Now, moving on, let's first I show you that the critical K star that allows you to move from the merit put space into the asset space, in this case is actually elementary. It's very easy. Is this K1 1 over B minus K2 1 over B, everything to the power of B, okay? Then what I need to do is compute this integral for the price of the compound merit put. And this is how it looks like. And I think the main, let's say, technical result of the paper is this one, is this theorem, which actually tells you how to compute this integral. Remember that regardless of what is written here, which is, I will get into details in a second, remember that the price under the log normal case depended on a bivariate normal. So in a way, you should have something similar here, a sort of bivariate something, okay? What you have is indeed this function, which is a special function, which is called upper hypergeometric function of the first kind, which is a sort of a bivariate hypergeometric. Okay, it is related to the bivariate hypergeometric function. More specifically, so the first line tells you how to compute the integral in general. It will be a function of this f1, which is the appel function. If in the specific case, you see mu equal m, which in the option world means if the compound option, if the compound merit put is issued at the money, this function becomes the usual hypergeometric function. And if we impose further that b is equal to a half, and remember that b is between 0 and 1, so a half is actually the middle point of the possible values, then this integral is actually elementary because it depends on the arctangent, which is an elementary function. In every calculator, scientific calculator, you will have the arctangent. So putting everything together, so we are able to compute the expectation, we are able to compute the probability because we know the distribution of this. We put everything together and what we have is in fact that you are able to price the compound merit put under this setting. and the price will essentially depend on this special function f1. Okay, so far so good. So at this point I have the merit put under like Black-Scholes economy and conjugate power Dagum, the compounded merit put under the Black-Scholes economy and under the conjugate power Dagum, which again you see it is sort of bivariate something. Now, what we don't really care about this compound merit put, we care about the compound option, so the compound call. And this is just how to show you that you can link compound merit put to calls in the following way. So we write the payoff of the compound merit put. First line, you do some manipulation, you sum and subtract K1, you do some grouping, and then you will recognize that what you end up is actually the payoff of a compound call struck at the difference of the strike, which is the mother like option is struck at K2. So you can write this replication essentially, and you can do the same for the put on call. And this is essentially how you would link call on calls and put on calls to the compound merit put. Let me just say briefly that the other, because there are other two compound options, there are the calls on puts and the puts on puts. I didn't investigate this much because I didn't need it for what I'm going to do after. But if you try to apply the exact same trick, it doesn't work, or at least, I mean, you would end up with option on random strikes, which is something that like I have not investigated. So at this, like I'm able to nicely connect compound merit puts just to calls on calls and puts on calls. Okay, now we get to the final part. So I'll be as fast as I can. So this is the part that you asked me at the beginning. This is the result that is what's called Whaley's decomposition. So on the left-hand side, you have the price of the American call written on an asset that will pay a known dividend at time T1. And you can statically replicate this with an European call struck on a strike call K star that you will determine with maturity T1, plus another call struck on K2 with maturity T2, minus a call on call in which the mother option, which is, let's say, the outer option, okay, is as maturity T2 and strike K2, which is written on an option with strike K star plus the minor K2, and it has maturity T1. This is in the paper of Whaley, and Roll himself show how you would find K star. Again, in the log normal case, this K star is not you need to compute this numerically. And moving forward, I write the exact same expression in terms of merit puts, and this is the only thing that since I have the price of the merit puts, this is what I care about, so I can directly use my results, and this is how it looks like. And so I have this first summand A, which is the price of one period merit put, which I have the price of this. Then B is the price of the compound. Sorry, C is the price of the compound merit put, which I have. What I don't have yet is the price of the 2-period merit put. And this is what I said at the beginning. The distribution at time 2t, if you have these increments which are conjugate power Dagum, is not conjugate power Dagum, but again you do a lot of calculations. Just I will skip this, is just for the sake of just to show student maybe how you would do this. The same under the measure Q hat, you would get this, and at the end of the day, this is the price of the 2-period merit put, which depend on the appel hypergeometric function as well, but it's not really bivariate because Here we used to have a variable. Now you have -1, but nevertheless, this is just this ugly expression. And if you put everything together, you get even a uglier expression of the pricing of this derivative. So like in the paper of, well, it's a series of 3 papers. That is why it's called Roll-Geske-Whaley formula, because Roll started, Geske came after, and then Wiley essentially corrected the mistakes in the first 2 papers. So the final result is from Wiley, and it gives the price of this derivative under the log normal case. This is, to the best of my knowledge, the first case where you are actually able to have a semi-analytical formulas for pricing this derivative under a different distribution. So I think this is, regardless of being useful or not useful, I think it's, I would say, a nice result to have achieved. But now I will conclude, and I should be on time, with the part that Peter liked the most, because it's true that we have an alternative pricing formula. Okay, but it's not, I mean, I think it is as ugly, if not even uglier, than the formula that you have in the Roll-Geske-Whaley formula, which of course depends on bivariate normal distributions, because you have compound options inside. What I care is, let's see for under which parameters this ugly formula may become something nicer. So we know that the 1 period merit put is always elementary, is the LP norm of strike and underline. Then if we take the compound merit put, it is at the money and B is equal to a half. As I said, this is also elementary because it depends on a square root and an arctangent. Surprisingly, very much surprising to me when I derived this, the 2 period merit put, which remember was this ugly formula, okay, if it is at the money and B is equal to a half, it is actually equal to pi over 2 times S0. So the last part that you need to find elementarity to have a formula, an American option pricing formula, which is elementary, is this K star. So the K star of the original pricing of the American would be found in this way, okay? The first line, you can arrange it as in the second line, and you can factor the different powers in this other way. This in general is not elementary for any P or any Q of this model. However, for some P it is. And this is just about, it is, as you, it's sort of in disguise, but what you have essentially is a polynomial equation. And we know that polynomial equations have elementary formulas for up to the 4th degree, okay? So for K equals, for P equal 2, 3, 4, 5, you add 5 because the summation goes to P minus 1, so this is actually a 4. So this formula would actually be elementary, becoming progressively uglier the more you go from 2 to 3 to 4 to 5. But let's say for B equal a half, which is P equal 2, it is the one on the left, which is not that bad. And this is actually the one that we care about, because the other formulas here were elementary for B equal a half. So this is the one that I'm going to use. So I plug everything in, okay? And what I've left to have something which is elementary is the compound merit put that we know it becomes elementary when it is issued at the money, which means that this condition 11 has to be satisfied. This corresponds to this equation that you can solve for D. So this formula is elementary if it is at the money, is equal to 2, and it is for a specific dividend. So this D star, which is 2 minus square root of 3 S0, which again, I think is very unrealistic as a value of dividend, because I'm saying that the dividend is about 30% of the price today, which is a very large dividend. But as the referee to this paper said, this is a nice mathematical exercise. And I think he put it this way, in a, just, it was a nice way to say that he didn't care, but I do. And at the end, if you plug everything in, you do your calculation, you get to the final result. That is, I think, what it is like, I think, surprising, because at the end of the day, this is an American option. And this is the price of the American option, the one that you see in the box. This is fully elementary, and it is just a rescaled version of the asset price. And to the best of my knowledge, there is no such way of I can think of American option which have nice, let's say, usually nicer. For example, the American cash or nothing. It's something that you can price semi-analytically, and the formula is relatively nice. But there is no formula for American option which is elementary, no matter how you put the parameters in, and not as simple. Because at the end of the day, we impose many conditions on different sides, but somehow when you put everything together, everything, like, let's say, turns up nicely and very interesting, at least to me and Pete. So to conclude and wrap up this long talk, we showed how you would price compound Mary puts, calls on calls, and puts on calls on this IAD Conjugate-Power Dagum increments. The distribution is consistent with neutral pricing and would allow for negative skewness and mild excess kurtosis. We show that for some parameters, the price are elementary, okay? And at the end, we apply this to finding an alternative to the Roll-Geske-Whaley formula, which is, to the best of my knowledge, the only one that is being proposed in the literature, okay? And we also show under which set of parameters this formula, which is the price of an American option, turns out to be elementary. And to conclude, when I was saying in the beginning, one of the restrictions that I had to put is that these increments are equally spaced. This is, of course, is a very strong restriction, but at the same time, digging in the math of this exotic function, appel function, and whatever, I found that there is actually a class of functions that if you iterate this n times, you know the final distribution. Well, you know how, at least you know how to compute the final integral. It's going to be another special function, but it's already there, okay? And in a sense, if you think that now you have n intervals, you can make them arbitrarily small, and under this specific case, then it doesn't matter that they are equally spaced. If they are small enough, I think it is a fairly, it is not such a big stretch as in this case. But as I said, like, this was the starting point of a longer project that I would say that I hope to carry on, like, in terms of, like, let's say, the legacy that Peter left about this, which I've always been, like, very fascinated about. And I still think, like, spoiler, like, the reason why I think Peter was very, like, keen on working the distribution, and the fact that you see that the price of the option lines up very well with LP norm, and that there is this sort of, this pricing seems to arise naturally from the payoff, is that because he believed that under this setting, maybe it's a little bit easier, or at least you can do something interesting when looking at American option, not just like this one, which is a very specific American option, but general American options. And this is all work for the future. So I thank you for your attention, and I welcome any questions or observations. So,
great, that's amazing. I do have one question, but I wanted to ask if anyone in the audience has any questions before I go. So I remember, when Peter was around, he, he's always trying to talk about this distribution and showing how amazing and convenient it is, for valuing these options. And I always marveled at the sort of beauty of the theory of it. But at the same time, I was wondering, and you've taken it to another level, of course, which is really nice to see, and really expands the attractiveness of the model. But the question I have is this to be usable? Is it something that can be sort of empirically validated, this choice of distribution?
Okay, so I think this is a very valid question. And the answer is the only work, except for this one, that uses the distribution is in Carr-Torricelli. On the finance.
Is in where, sorry?
Is in Carr-Torricelli Finance and Stochastic, okay?
Okay.
In that paper, they look and they try to fit option prices like to this conjugate power Dagum distribution, alongside measuring the performance of two other, like, let's say, competing, which is the variant gamma and the BNF jump model. And what they say is that I would say that it does the best that it can for being just a model with one parameter. The other models have 3 to 4 parameters, so they are able to fit in a, of course, they have more degrees of freedom to fit the implied volatility surface. And so, like, to answer your question, is it usable? I would say that in the state that it is, you might be using other models because they are more able to reproduce what you observe in the market. At the same time, I'm aware of Lorenzo Torricelli working on a model which is inspired on this conjugate power Dagum model that adds some extra parameters to allow some more flexibility to model this. So I think not all hope is lost. At the same time, I might say that the model that he has been using is the one that is in their paper that I think is you get somehow. Peter always used to say this: if you start on Black and Scholes, you start with a simple process, which is a geometric Brownian motion, and you end up with, let's say, a relatively ugly formula because it's non-elementary. Okay. What they do in the other paper is that you start with a nice elementary formula, but what they end up is a process which is very, I would say, very ugly, because it's a time inhomogeneous additive process. So it is something that needs a lot also of work to be calibrated. So, but this is the reason why they get to this process is that they are not willing to trade off what I trade off. So I said that I was willing to give up a different distribution at the final time for keeping the increments with the same, but they have to do the reverse. So essentially they have increments which are not a Levy process, okay? So they are not IID, but they are able to preserve the final pricing formula. What I would do, like what I'm trying to do and I will be doing, is trying to do this, like keep the increments. So keep the price ratio conjugate and end up with whatever distribution I have at the end. So they are IID. And this type of process, well, first of all, it still don't work, but this is something that has never been tested on real data, so I cannot really answer that.
Okay, well, that's certainly very helpful. Thank you for the explanation.
Thank you.
Any final questions? I know we don't usually go too much past the hour, but I'm sure we could squeeze in one more question if necessary.
I have a question, but I don't want to take anybody's more time. If somebody else has one, I'll defer to them. Dave.
Okay, anyone other than Leon? I guess you're on, Leon.
Federico, this idea about this K star, that's what's confusing me. So what you're saying, let's say I take a very simple case of a compound option where the expiries are, ratio of 2 to 1, right? So it's an option, a 3-month option to buy to buy an option that expires 3 months later, right?
Mhm.
So you're saying that if you find this K star, you can somehow eliminate the compoundness? So
No,
to
no,
speak?
no, no, no.
Is that
This
wrong?
is the K star is the so you would exercise the compound option if the price when it expires is less than your strike.
Right, correct.
Okay.
Or it's
What
more,
you have in the contract is
Right.
the strike. You want to rephrase this event not in terms of the price of the option underlying, but in
Right.
terms of the price of underlying.
They're
In
like,
terms of
understood,
S.
yes, understood, right.
So K star is the correspondent value of K that was in terms of the option price, but translated into the price of the underlying.
So in other words, K star is what would the value of the underlying have to be
Yes,
for
to
me to
the option to
exercise
be
the
exercised.
compound option?
Yes.
But but of course, you didn't think about it, right? In a regular Black-Scholes world, whether I can't say at the expiration date of the over option what I exercise, because it depends not only on the underlying level, but also the implied volatility, of course, right? I mean,
Well, in the Black-Scholes model, you assume that
Right.
volatility is constant, so you don't have such a big difficulty in a way.
yeah, so if you sort of said to me, if I have an option to buy a call at $3, 3 months from today, I know what stock price will lead me to a price above $3, basically, right?
Yes, this is exactly the point. Yes, which is, I mean, again, but this is how the Jeske formula for pricing compound. This is, I would say, this is very standard in compound option literature. This is the way you would find this K star, because at the end of the day, the distribute. It's easier to work with distribution of S than with the distribution
option.
of the option.
Of course,
okay?
of course, right, right.
So that's just the stretch. Of course, in fact, compound option for this specific, there is a paper in 1993 by Sommers and someone on analysis of applied probability, which actually contests an idea of the famous paper of Geman Madan about the change of measure, because in the paper say that even under stochastic interest rate and stochastic volatility, their technique would work for compound options. And actually, this is not true. Under stochastic volatility or stochastic interest rate, the compound option problem, it's not as solvable just for this reason, because you are not able to identify this K star in such a simple way.
It's funny, in the bond market world I'm familiar with more, it's sort of like saying, well, let's say you want to lock in a rate where you enable somebody to issue a callable bond at a future date, right? So if you do that, you're basically locking in for that person the combination of the market yield level as well as the implied volatility.
Yes.
But that, of course, that's purely empirical. Nobody's sort of saying that I'm not in stochastic vol, I'm just sort of like saying that it's a two-factor problem, right?
Yes. Yes.
So, yeah, but that's actually people have thought about that problem in the bond market, right? How you could lock in basically like a forward contract on a callable rate, essentially, right? How would you price that? How would you agree to somebody to award them a fixed rate to issue callable money at some future date, right?
Yeah.
Right. Thank you very much. Wonderful.
Thank
Very
you.
interesting.
Yes, thank you so much. We really appreciate you spending the time, Federico, and congratulations on the progress. And we look forward to seeing the new results when they come out.
Yes. Thank you very much.
Okay. Have a good evening.
You too.
Thank you, everyone.
Bye, David.